My name's Timothy Fenn. I'm a postdoc in the Simbios program here, and I work primarily with Vijay Pandey. So crystallography is the predominant technique by which the atomic structure of a molecule can be determined. And it's essentially a repeating unit of these molecules that forms a crystal. Diamond is the perfect example. But for big molecules like proteins, which is an important area of study for crystallography, a lot of the parts of the protein can be floppy or disordered. And that's actually a bit of a problem, because typically the parts that are floppy or disordered are the parts that can be involved in function or transmitting signals through the protein. So those are the parts that we're really sort of interested in. But up until now, scientists haven't had a good way to really describe the floppy parts, the dynamics, the disorder that can actually be part of a crystal. So my work with Vijay Pandey here has been to combine what his real expertise in protein dynamics and simulation with the experimental information in X-ray crystallography to really come up with a full description of what's going on in the crystal, so we can talk about which parts are floppy and how floppy they are and what that might mean for how the protein works. This is ubiquitin, which is actually binds to many proteins and is involved in a lot of cellular signaling processes. So understanding its dynamics has actually been the focus of a number of studies. And, the mesh is actually the experimental information, and the model that we build into this mesh is shown in like the stick representation. But you can see that there's parts of the mesh where the sticks go right through the mesh, and it's very well defined. But there are parts here where there's this big loop where the density isn't very well defined. So those are parts where we've never really been able to say exactly what's going on. And with the technique that I've been working on, we can actually come up with a full description of the floppiness in this part of the protein. And you can sort of see that here. And it's a little easier if I turn that off. So we can actually fully describe the dynamics that are going on in this part of the protein. And you can see the rest of it is a little more stable and static as the data restrains it, in a sense.